as Mark said, I've been in the industry now for about 20 years, and in the HVAC side, but in the pumping industry for about 32 years. And I started with Armstrong, I left, and then I came back. And in that interim, I was in water and wastewater applications. And so one of the nice things of coming back to Armstrong was when I went to a site, I didn't come home smelling like sludge anymore. So a bit of change there. A lot of information imparted today, and what I'd like to do is tell you what I have learned over the last 20 years. When Andrew called me up and said, okay, we're going to have you present, and he says, okay, this is the topic, decarbonization, sustainability, and efficiency. I said, that's great. I've got 4 of your slides I'm going to plagiarize. And at the same time, I've plagiarized some of the slides from Train as well. So the point here being is that a lot of this information is out there. And I've done over 7,000 speaking engagements in my career. And what I found a lot of times is you've got to simplify the message so that you can get it to the lowest common denominator so everybody understands. And that starts with me. So you're in for a bit of a trip because I'm left-handed and I'm dyslexic, so I don't know what side of my brain is working at any given time when I'm talking. Anyway, so outlining the roadmap. Everybody has seen this. We're looking at decarbonization, sustainability, electrification, and efficiency. It's as simple as that. But there's something to think about. First of all, perception does not meet reality. Energy efficiency is a key priority. And innovation is required for reduction. City of Ottawa made a point now of talking about their structure and their game plan. And if you listen to what they said, all the cities are doing this. So first of all, we have a built environment in our buildings, and we're going to look at slides of this, where we have 39% of our carbon reduction, our energy is consumed there. And then there's almost 30% in transportation. And that transportation right now is with gas. And so we want to move that energy source to electrification. Think about that. And right now, today, when we have peak load demands on buildings, we ding them for power consumption. And we're going to increase that power consumption by almost 200% on the entire grid. So we have to look at innovations in this industry and how we can do things different. So if you're looking at, in terms of progress, as much as we think we're headed in the right direction, it is slow. It needs to speed up by 7 times. And in terms of energy efficiency as a key priority, energy efficiency represents more than 40% of the emissions abatement required by 2040. So that means that we have to eke out efficiencies in our buildings by up to 40% to help deal with the load that's coming on. So in terms of innovations required, building heating and cooling systems are a fundamental opportunity to find where that energy abatement can happen. In terms of the built environment then, a very similar slide to earlier presentations, but building operations represent 28% of all the carbon we're producing. The other 11% are in embedded carbon. And like I said, plagiarized. I took this from a colleague at Train. But if you look, here are the 4 key pillars. Matt said, energy efficiency, electrification, refrigerant management, and renewable energy. The way I always look about refrigerant management then is fundamentally in our industry, if we're looking at electrification and we're moving from boilers and we're moving towards heat pump technology, to me, refrigerant management is understanding the refrigeration cycle and how it works. And that's going to be key in terms of the moving forward in this journey. So, a decarbonization path. Well, first of all, you need to develop a strategic plan. First portion of that plan revolves around energy efficiency and energy recovery in your systems. That's key. So we talked about thermal storage, heat wheels, that type of application. But then alternative fuel for transportation. One of the other big things in existing buildings is to remove all steam end uses. So moving away from steam production. Then thermal energy, renewable energies, understanding utility grid capacity and rates, energy storage, batteries. Then we have to also leave space for understanding that there are emerging technologies that will be incorporated in this strategic plan. The way we're doing things today are going to change as compared to what we're doing 10 years from now. And then finally, that is our path moving towards a carbon neutral energy system. But the other key here is operations and maintenance. We were at a building in downtown Ottawa yesterday in a site visit. And it's the same factor with a lot of property management firms. The operators that are in those buildings today are starting to move towards retirement. And it's hard to find people to replace. And all of that operation knowledge is moving out. It's not sexy to be a building operator anymore. But the point being here then is with operations and maintenance is how do you put that or capture that knowledge, or how do you improve the performance of your building on a continuous basis? So in that strategic plan, after energy efficiency, when we talk about energy recovery, we're looking at energy recovery from simultaneous heating and cooling systems. Trane has chillers that will do simultaneous heating and cooling applications. We convert the DX systems to cooling systems or chilled water. Connect process loops to chilled water, and what that means is now we're capturing more of that thermal energy. Convert steam heating systems to hot water, and reducing hot water systems down to 140 degrees or lower. And when Matt mentioned the Noventa project in downtown Toronto, Western Hospital, one of the key things that they did there is that the whole healthcare facility actually moved to low temp hot water. They're running at 115 degrees. The capital investment on that, $15 million on replacement of fan coils in the ventilation system. Why? You need the increase in surface area. So, and the point being here is now, as we get into this, first of all, our industry is quite simple. In our buildings, we're either putting energy into the building for heating or taking energy out for cooling. That's the way I often explain it. It's not a very complex process when you come to think about it. Pathways then are, if we're looking at it as a complete solution then, envelope upgrade, HVAC upgrade, thermal exchange and implementation, and then energy recovery. When we look at upgrades, we're looking at windows, insulation, wall assembly, infiltration minimization, shading. So that's looking at the upgrade of the building itself, of the envelope, the box. The HVAC upgrade, ventilation distribution, introduction of heat pump technology, advanced energy transfer stations, if we're looking at district energy applications, and then advanced dynamic controls and systems optimization. In terms of thermal exchange, then, electrification with high COP equipment, and thermal storage potential in ground loops, or thermal storage. Now, in all of this, the only thing I'm really going to talk about is the control side and advanced optimization and what that's all about. In perspective, Armstrong has been in this industry, but there are other key players. And if I mention them, JCI with CPO 30, Optimum Energy, Continual, Convergent, they are all offering very similar solutions in this. The challenge is that when we come up to any one of these organizations approach the marketplace, and they say, well, we can reduce your power consumption on your chilled water plant by anywhere from 20 to 40%. The question is how? And it's in the black box. And they're saying, well, can you explain it? That's what I'm here to do. So, and the reason I am free to say there are other players in this market, first of all, there's always the engineer's side of we need 3 names on it. But to give you reflection, in the built environment, and this is just rough numbers, globally we have 7,000 high-rise buildings. In the US, if you're looking at resorts, healthcare, and universities, we have 54,000 buildings. In Canada, we have 3,300 buildings. So there's more than enough opportunity in the marketplace for all the players to pursue this. And that's the point. And that's why, but what we'd like to do here is give you an understanding of how this works so there is no mystery in the black box. And fundamentally, HVAC controls are simply based on second and third year mechanical engineering principles. Fluid dynamics, heat transfer, and thermodynamics. Once you understand those principles, all we're doing is looking at digitalization and then demand-based controls. And we're going to get into more detail on what digitalization and demand-based controls are and how where that pathway leads. But if we look at fluid dynamics, it's simply understanding the affinity laws or the fan laws. And we have now moved from a constant speed world to variable speed applications. Variable speed drives on our chillers, on our pumps, and on our fans. So if you drop the speed of a rotating piece of equipment, the energy saved is the cubed of the squared. ASHRAE 90.1 stipulation on how to lay out your chilled water loop basically wants you to drop your energy consumption by 70% at 50% load. So understanding that. But the other key here is understanding how rotating equipment, pumps, work in variable flow and what the control curve is. That's one of the key fundamentals. So understanding the control curve and the affinity laws. Then, and I like putting this up because this is just the simple math. In terms of heat transfer, if you look, we have the load equation. Load is equal to flow times 500, which is a constant, times delta T. Very simple. At the same time, heat transfer, the rate of heat transfer is equal to the surface area times the temperature, the LMTD, or the temperature approach. Now, if you increase or decrease that temperature approach, your LMTD, you're trying to move more energy from one side to another. What does that affect? A, the surface area. What happened at Toronto Western? Less temperature, more surface area. But at the same time then, if you look at the bottom equation, which is simple pump equation, the brake horsepower required by a pump is equal to the flow times the head divided by 3960 times the efficiency. And what's key in all of this is that in our typical control strategies, we're operating off of set points and speed base. But if you look at here, and if you look at the math, if you're able to factor in the efficiency of your equipment, the higher the efficiency at its operating point, the less power you're going to consume. And that's why I show the math here, because it's all straightforward. If you understand the math, this is where you're going to when you start looking at optimization. And then lastly, the refrigeration cycle. And simply put, there are 3 ways to reduce chiller load in a simple form. It's load reduction, it's lowering the entering condenser water temperature, or raising the chilled water temperature set point. And if you look at the graph then, is because when you lower the condenser water temperature or raise the evaporator condenser, the evaporative temperature side, all you're doing is lightening the load on the compressor, and the compressor has to do less lift. That's the process here. So understanding those fundamentals, first and foremost, are the key to when you start talking about what optimization is all about. Now we talk about digitalization. And the key here, and this is where the industry is moving towards, is that instead of basing your control simply on speeds, knowing that piece of equipment can speed up or slow down, you're creating a digital twin or a digital model of that piece of equipment that outlines its performance characteristics. Now, if you look at the bottom one, that's for a 400-ton chiller, and we have the load and the kilowatt per ton based on load. Now, because we have that data set, we know when to stage the equipment based on load, and if we have multiple pieces of equipment in parallel, now we can spread the load across. So instead of running one chiller to 100% and drawing 0.596 kilowatts per ton, we split that load, and if 2 chillers are doing it at 50%, what's your load there? It's at 0.35 kilowatts per ton. You're still doing the same amount, 2 chillers are operating, but now your kilowatt per ton performance has dropped drastically. Now, how is the controls done? Fundamentally is we are moving away from a set point control, PID loops, to demand-based controls. And when we talk about demand-based controls, what we're saying is we respond directly to the process state to provide an operating configuration that is predetermined. And I'll get into a bit more detail into what that means in a few slides. So what is HVAC plant optimization? Well, if you look at the traditional scenario, what you have are PID loops in that setup. And if you look at on the pump side, you have a sensor, a DP sensor located somewhere remotely in the system. When a valve opens or closes, there is pressure on either side of that sensor, and there's a diaphragm in the middle. That diaphragm moves from its zero set point, and as a result, it sends a signal to the drive to either speed up or slow down the pump. The pump doesn't know what flow it has to give or what head it has to produce. All it knows is it either has to speed up or slow down to get to that set point. And then once it gets to that set point, you're back to a stable state. Now, if you look at the entire chilled water plant, it's multiple disconnected set points. You have the building load. The chilled water pumps respond to the building load. The chillers then respond to the demand from the chilled water pumps, and then the condenser loop responds to the demand for the chillers. They're multiple disconnected set points. We're trying to achieve part load comfort, but we're always hunting to get back to a stable state. And so it's a silo operation and does not take into account plant efficiency. The sequencing then is parallel equipment staging up or down. It's speed-based controls, and it's all silo. So capacity-based sequencing, PID feedback, and ambient resets. So when we get into optimization, what we're doing is we're looking at a demand-based control solution in a central plant as one complete system, not individual autonomous components. And what we're trying to do is to move a thermal load from one potential to another using the least amount of power. And the point I make here is that our industry, when we look at what we're trying to do, is all we're doing is moving thermal energy from inside the building to outside, or through a heat source to inside the room. All it is the movement of thermal energy. When we're moving that thermal energy, we are using mechanical equipment to move that thermal energy. In a chilled water plant, it's the pumps, it's the fans, it's the chiller compressor, it's the condenser water pumps, and it's the cooling tower fans. We want to look at that as a complete system. So if you're looking at it, the system makeup is the air handler, the fan coils, the chilled water pumps, the chiller with the evaporator and condenser barrel, the compressor, condenser water pumps, cooling tower fans. Now, if you look at it in second and third year mechanical engineering, it's heat transfer, affinity laws, heat transfer, refrigeration cycle, affinity laws or fan laws, heat transfer. That's the logic. That's what we're doing. So how does this work? Well, the building load and the ambient outdoor conditions are determined, enabling a digital model to be used for operating configurations that optimize the system performance. So basically, now the system becomes an equation, and you need to know what is the load inside the building. How many BTUs are we trying to move from inside the building to outside or to somewhere else? And then, what are the ambient outdoor conditions? So what's the temperature outside? Because the key here then is understanding that the way a cooling tower is designed is that it has an ambient approach temperature to the atmosphere. And that's usually either 5 degrees or 7.5 degrees. So if you understand that and you understand the mentality of typical controls, now take a step back. We always want to have the lowest possible temperature entering the condenser side of the chiller because we want to lower the lift. A typical controls contractor will set that at 65 or 75 degrees depending on what the chiller manufacturer specifies. But if it's 95 degrees outside, you're never going to get to 75 degrees. Your fans don't know that. Your fans are going to run at 100%. And no matter, they can run 120%, but you are not going to move any more thermal energy other than what that approach is designed for. And that's one of the keys. So now, if we know what the building load is, we know the ambient outdoor conditions, especially on the condenser side, we know where to operate the equipment and the speeds that they can operate at. So what is demand-based controls? Well, it responds directly to the process state to provide an operating configuration that is predetermined. So based on the indoor load and the outdoor conditions, we have already predetermined where to operate the equipment based on that situation. And this is based on a feed-forward control or demand logic requirement. So basically, all we're doing is now, from the load and the ambient conditions, we now have maps on the pieces of equipment. Because we have those maps and we have the efficiencies associated with those pieces of equipment, we will know how to stage them at their best efficiency points. So optimization is just digitalization. We have the digital maps. What we're really doing is the system, we're mapping the tons of cooling and the electrical power. That's the association. So how many tons of cooling and how much power are we consuming? It's all performance curve based. It's a relation between heat transfer and power consumed. And it relates the building demand and power required to move that thermal load from inside the building to outside. So how much power do I need to move that thermal load? That's what we're doing here. What we do then is that if we're looking at each piece of equipment, we're trying to get down to the lowest kilowatt per ton. And a colleague of mine explained this in the most eloquent of ways. This logic here is almost based on supply and demand. So first of all, if I have to add 1 kilowatt of more power to move a certain unit of thermal energy, where is it best to put it? And what happens now is when the plant is operating, the logic will do a trade-off. Is it more efficient to add the power to the chilled water pumps, or is it more efficient to add it to the chiller? Where am I going to get the best bang for my buck? That's what the logic is doing. So the staging now is based on efficiency. We're looking at condenser water relief. I'm going to qualify that because we're letting the condenser water temperature float in the logic now. But we're using digitalization and we're using that demand-based controls or the logic there. So if you look at the relationship then now, and this is fundamental, it highlights the relationship between a chiller's COP performance and its entering condenser water temperature. Now that chiller has an efficiency curve or a COP curve associated with it, coefficient of performance. I got to stop using acronyms myself too. If I have a low ambient day, it's 13 degrees outside, that means I can drive my entering condenser water temperature down. And if you look, I can achieve a peak efficiency of almost, in this case, around 13, a COP of 13, at around 45% chiller load. Conversely, if it's 18 degrees, best COP is around 10, and it's over at 50. High ambient day, 29 degrees, COP is around 7, but it's moved to maybe around 38%. The point being is that now, if you're looking, we are mapping the relationship between the tower's performance, or the entering condenser water temperature, and the chiller's performance, and a natural curve or best staging point starts to develop with that data set. And so now, based on ambient, load, chiller, we know where best to stage them in part load and how to split that load up. Graph here, a graphic that highlights this, is if you're looking at traditional capacity-based staging then, or sequencing, you've got a lead lag and a second lag chiller. First chiller, if we're looking at capacity, we're at 50% of building load. We're going to take that first chiller to 100%. If we do the efficiency-based staging, we're actually splitting the load. And you'll see now the COP is actually higher. If the load increases, second chiller stage is on, whereas we are still splitting the load between the two. And then if it goes to 100%, second chiller goes to 100%, but now and this is especially true in a lot of N+1 applications, what the logic does is if I have a redundant piece of asset there, I'll bring that piece of equipment on. And now I'm splitting that load between 3 units as opposed to 2. I'm improving my COP. And the logic here is, remember, what are we doing with our chillers? We're moving thermal energy. All we've done in this is we're utilizing the surface area now we have that's sitting in that idle asset. More surface area, unloading the chiller a little bit. The key here then is that there's significant energy savings opportunity, especially on design day considerations, on peak load, where if you look at the data set that's provided, you can save up to 10% on your energy consumption on your chillers on that design day if you have redundancy in your equipment or an N+1 consideration. And I like bringing up the performance maps here. This map is based on 10% intervals on AHRI relief. So, if we're looking at condenser water temperatures anywhere from 94 to 74, you'll have your kilowatts per ton anywhere 0.59, 6 at 100% down to about 0.30 at 50%. And then conversely, if we're looking at constant condenser temperature, again, even at constant condenser temperature, at 100%, you're at 0.59. At 50%, you're at 0.51. 10% savings. Now, the reason I bring this information up is that this is the data set, or this is the digitalization that's required for optimization. What happens is you take the data sets, you create digital models of your equipment. Once you have those digital models, you know how to stage that equipment based on load and demand. Secondly, then, on the tower side, and this is a big functional difference, is that typically the designs are 1 tower to 1 chiller. When you have 1 tower to 1 chiller, what that means is that you have to run that fan at 100%. What we're doing here is we're utilizing the tower's surface area that's available to us. So if we have 3 towers at part load, we will utilize all 3 towers. What happens then is that now that you've increased the surface area, you can drive down the fan speed. And remember, the affinity laws. Dropping down the speed of a piece of rotating equipment saves the energy by the cubed of the squared. So you're basically at 50%, you're saving 70% of the power on that fan. And a real case example of that is we implemented this technology at the Federal Reserve in downtown Manhattan. This was years back. And the plant operators were looking at the sequencing, and they were shaking their heads, and they said, no, this isn't going to work. This isn't going to work. And the beauty of the logic is that you can turn it on and turn it off. And when the control logic was off, the plant was running at 0.94 kilowatts per ton. They had 1 fan running at around 90% of speed, and they had the condenser water pump running at about 60%. When they turned the logic on, the 3 fans were engaged, but the fans were operating at 60% of speed, and the pump speed went up to 90%. But the energy savings, the plant went from a 0.94 down to an 8.3 in 5 minutes, kilowatts per ton. And it was the ability to sequence the equipment. So what we're doing is that we're utilizing the surface area on the system, And one of the things that's unique here that differentiates is that the way the logic is working is that on the tower side, you're dissipating energy through sensible heat and through the latent heat of evaporation. Now, what we're able to do is that we will calculate an equivalent surface area value to the latent heat of evaporation. So say, for example, my tower is 1,000 square feet, and the equivalent latent heat is equal to 300 square feet. So now we know fictitiously that we have 1,300 square feet of surface area, and that affords the ability for the calculation to be simplified and drive down that fan speed so that we're taking it to where it can be to meet the ambient conditions out there. And that's why we would let the condenser water temperature float in that system. But that's where the logic works. So what we're doing is moving from traditional to efficiency-based or demand-based controls, which is efficiency-based staging, digitalization, and demand-based controls. But what is the future? Well, the future is now. And this is where when we start talking about AI, digital twins, machine learning, artificial intelligence, and continuous optimized self-commissioning. What that means is now, with AI, the system can learn and adapt and continuously optimizes. What it's doing, it's gathering operating and performance data. Everybody wants data. Now that you have that data, now remember we showed the original performance maps. The way the system is first set up is that you set up your performance maps based on published data. System starts operating, you have a digital twin. You look at your performance data and look at the actual performance of the equipment. Now you're cross-referencing. Is this the data in alignment? If not, do we update those performance maps? We continuously do that. We compare the observed performance and the modeled performance, and it advises the availability for capacity in terms of real conditions. So, digital twin and machine learning, what we're doing now is that the equipment starts to learn how it's operating. And that learning then updates those digital maps. The challenge then is that if you look at this now, you've got digital updates on your pumps, on your chillers, on your towers, and that becomes a multi-dimensional digital performance map. The last time we were trying to calculate it, it's actually 26-dimensional. So if you look at that matrix, there's 26 dimensions in that in terms of the data that's available and in terms of outlining the performance of the system. But once it collects that data, it's able to adapt. And it continuously then commissions or recommissions or improves the performance of the system. That's where the logic is coming into. So that digital twin updates the control maps, and it becomes an all-logic cycle moving through for optimized performance. And the key then here is that a lot of our plants will drift over time. Major factor in drift is fouling. But because we're collecting that data, we're able to also then do diagnostics on the system, see for fouling, see anomalies in the system. There's another case in point where we had a project and we weren't getting the performance that we expected. And the long and short of it was that through the analytics, we were able to determine, and this was an 8,000-ton plant, one of the chillers, approximately 20% of the evaporative tubes were plugged. You don't get that from speed-based set point control scenarios. The other portion there was, again, we were looking at the system, and we had a pretty high power consumption on the pump side, and we were looking at the head, and the head required was about 20% greater than what we thought it should be. Through the diagnostics, we actually determined that an MRI loop in the system, when that MRI machine was up and running and it was drawing cooling, it created that increased pressure requirement in the system. End result, we put a pony pump in that loop, and the overall head on the primary loop dropped by 20% then. So that's where, walking through here is optimization is strictly demand-based controls with performance maps that factor in efficiency. But the opportunity is that now with those control strategies, it's being able to collect that data and do continuous diagnostics on your system so you maintain that peak performance. And that's what the industry is going to. So that's all I have to say. Thanks. Any questions?
Yeah, so I guess there's probably a sweet spot, a size of plant where it makes sense. I mean, obviously, I think bigger is probably, the economics get better. 8,000-ton plant, that's a good size plant. Is there kind of a minimum plant size?
Now, 400 tons.
Yeah.
So I'm going to put my Armstrong hat on now.
Yeah,
it's in the industry side. Typically, when we talk about optimization, we're looking at designs with equipment running in parallel. And that's the highlight, so that you're able to do the efficiency-based staging. And we would look at around an 800-ton plant or larger, where there'd be it'd be an economic solution. A lot of the plants that I'm involved in are of larger capacity, anywhere from 5,000 tons to 8,000 tons. Mm-hmm. The largest that we've done was a casino in Hong Kong that was actually 32,000 tons.
Wow.
So, and there's the economy of scale there. But with that being said, I and a colleague are now working on 2 projects where it's a single chiller application and they're 400 tons. And the reason being is that, I'll throw the brand, they've got smart units in there, and they're 500 tons, and he's got 5 compressors on there. But the way they have it set up right now is that even at part load, the chiller is running at full capacity. So being able to collect the data set helps you identify. And so now it's not strictly on the chiller side, but there's the tower optimization opportunity and the chilled water side of the opportunity. And the key to part of this is that even though that we were talking about chiller plant, a chiller plant scenario, this technology is applicable to anywhere where we're moving thermal energy. Heat pumps, heat recovery, incorporating geo exchange, all of it. Because at the end of the day, the way I explain it is all we're doing is we're moving thermal energy from one place to another. And as we move through the pathway of decarbonization, we want to recycle that energy continuously, right? Latent, it's heat of evaporation, heat of solidification, right? So all we're doing now is if I don't need it here, I'm going to move it here. Here's my heating load, here's my cooling load. The reason I bring in surface area, though, is that now, as we move to low temperature systems, that's going to affect cost greatly. 15 million on fan coils, you know, but there is an ROI associated with it. So that becomes part of the discussion, is like, we have to stop looking at, I'm a pump manufacturer, there's a chiller manufacturer, there's a tower manufacturer, there's my fan coils. It's a system, right? You don't buy a car and you have mismatched tires. Like, one of the things, the way I like explaining this technology is, my son's a service tech at Audi. And if you take a 2-liter turbo from the factory, it comes with 225 horsepower from the factory. Change the chip, and you get 350 horsepower, and you've done nothing mechanically to the engine other than changing the mapping. It's the same thing here. Get the maps, put the maps in, and then you play with the maps, and that's where the AI is going. And that's going to afford us a very cost-effective way of starting to do some energy abatement without the requirement of doing drastic upgrades first and getting the data. So, thanks.